Okay, so today I've got the UltraCAPs hooked up, two 16-volt UltraCAP battery or capacitor banks in series, and I'm going to put 24 volts approximately across this pair. And you can see I still have 5 volts left over from previous charging, and I'm even bleeding off, but this, it's 20,000 ohms. That's going to take a long time to bleed. We could use a smaller one to bleed faster, but I'm going to charge it up anyway. So I'm going to use Excelnet PWM output through inductors to the cap, which acts like a short to charge up. And then I'm going to switch over to the ME3 to drive. Normally we drive 3 motors for the same quiescent current, 24 volts, maybe less than 100 milliamps of current. When this gets down to 14 volts, there's a undervoltage shutdown, but apparently I can still talk to it even down to like 6 or 7 volts. This is the Nano. I'll test this next. This can operate down to 9 volts, run up to 90 volts. There's a 180 volt version too. Anyways, I got the same setup here for the battery charger we used in the previous video, a capacitor to do a safe charge. But let's take a look at going from 330 or 3,300 microfarads to 58 farads times 2. And let's see how much energy that is. So we got your normal power, volts and amps, right? It's going to be power. And then, that's joules per second is watts, or said another way, you got so much power and over time, so the integral of the power over time, so P dt. And so you've got these two equations, one for the integral of power, and then you have another equation for power on the capacitor. So the voltage times the capacitance times the change in voltage over the change in time. So you're charging up the cap, right? So you take these two together, you replace the power here with this, and you got n times dt. The capacitance is a constant, so it comes out. And now we're going to integrate the voltage. The dt's cancel, right? So you're just left with the voltage times the change in voltage. And now we're going to integrate the voltage squared. Okay, so voltage squared, it comes out and you get 1/2. So that's the process of integral. It's like the derivative, but it's the inverse function. Anyways, this is the derivation of 1/2 CV squared. And notice that the square of the voltage times the capacitance. And then you got to take half of it. So I've got two 58 farad capacitors, right? And I multiplied that by 2. And then I'm going to charge it up to like 25 volts times 25 volts. So that's voltage squared. And I get 72,500. Don't forget to divide by 2. 36,250 joules. So the rate at which you use that energy is, joules per second will be the watts that you're sucking out of the thing. So things that you power, like LEDs and encoders and halls, all this stuff takes power, and plus the motor, right? Plus the drive, just to keep its brains alive. So I'm going to charge this cap up here. Hit record. I've got a 32 volt supply. It's 216 caps, so I feel safe with that. So let's start with 8 amps. Oh, I got to enable it. Pull down. Here we go. We're starting to charge up. Yeah, see the voltage droops when you enable it. So I want no negative current. I've got diodes to protect myself too. I made sure I hooked up the cap. I did a test cap first before I hooked this up. And we can see Oh, it's charged. It's still collecting data here. I've got half charged. All right, let's lower the current here. Let's just do 4 amps. I'm getting an undervoltage shutdown. Okay, so we're back to charging again. So we can see the so charging up. We have pulse width going through the inductors to the cap, and the voltage DC's charging. So I'm still charging up. I was drooping on my power supply, so you can see the effect of what happens when you get to the under voltage. So my charger, the voltage was weak on it. Let's do an immediate trigger and see if we can record this. So as I'm drooping, I'm going to goose it up a little bit. Try to, you see the ripple. This is just an unregulated power supply. So, here's your DC bus drooping down when you're delivering all that current. And I'm approaching 22 volts now. Watching the meter here. I do not want to exceed 32. I got a 50-second trace time so we can see what happens over time. And we're still delivering 4 amps. So a nice slow charge. The cap bank can take 15 amps continuous. Maybe a little bit more peak. Okay, and that's sufficient charge there. The voltage terminal got up to like 28 volts. So on average 27. So that's good. Now we'll shift over to the other drive. Okay, so I took the bleed resistor off, and I hooked up the ME3. So I got the 3-axis drive. I've got a motor running. There's an encoder with Halls and incremental. And so that's probably about 80 milliamps at 5 volts here. So that's the power to the feedback. Halls by themselves are more efficient. So maybe you get like 30 milliamp Halls and do everything from just the Halls. I got a bunch of LEDs and there's a bunch of chips on here. So there's some consumption of power. But I'm running the motor. And I'm consuming some charge off of the capacitor bank, but I'm still holding the 25 volts. And so I'm going to monitor with CME here. We can monitor the voltage. Yeah, so 25 volts still. The interesting thing, while you're delivering volts and amps, when you're accelerating and running, your regen that comes back is just dissipating, just charging up the cap again. So got my motor hooked up and running it back and forth. I removed the bleed resistor and connected the power to the ME3. The ME3 is being run off of less than 24 volts now. I've been running for a little while, and it's starting to bleed off the cap. So the energy, some energy goes to the drive, a little quiescent current. But the advantage of the ME3 is that it's one quiescent current for 3 axes, so it's a more efficient model. The Nano is probably pretty efficient too. This ME3 shuts down at 14 volts. The Nano can go down to 9 volts, so this can stay alive on a lower voltage. But you get some watts in the drives. You get some watts in the lights and the chips that are on the board. Maybe this has less chips, so there's less watts. The motor dissipates watts I squared times the resistance of the winding. So choose a winding that has a low on resistance. There's also a commutating encoder here. Maybe it's like 100 milliamps at 5 volts, but you could run off just Halls. So maybe that's 30 milliamps at 5 volts, so much more efficient with just Halls. And we, of course, can control commutation. And it's a little bumpy ride when you're going slow, but it should be sufficient for most applications. Moving a couple axes around in a servo mode on a drone or a mobile vehicle. Okay, so we're going to take a look at connected to the drive. You can see on the control panel, we're bleeding off a little bit here. We can watch the voltage droop. The drive, of course, has a temperature, so a little bit above room temperature here. But you can see with this profile, I'm starting to get a voltage limit. So as the voltage droops down, you'll have to, the terminal voltage servo here is bumping into the voltage limit here. We're going to have to slow things down a little bit. So let's put in a little bit slower and then see if that, so a motor with a low back EMF would be beneficial. That would also have a low torque constant. So yeah, so at this voltage, we can maintain this speed, 24 volts at 1,000 RPM. So as the system droops, eventually we'll get to 14 volts. You'll have an under voltage condition. If you get voltage limited constantly while you're moving, then you'll get a following error and you'll shut down. So as the voltage goes lower and lower, you may want to reduce your speed so you can monitor the voltage and reduce your profile velocity to fit. So, when your battery is fully charged, you can run around. As you lose charge and your voltage droops, maybe you want to conserve energy. I can go a little bit further if I just go slower, right, without a following error, without using up as much volts and amps or watts. I mean, eventually you get down to the static friction, and then you're going to use up the current. Also, the XL and D cell takes current. There's not much of a load here, but I'm going to increase the current draw. One advantage is you pull current for acceleration, but then you dump it back as regen onto the cap. So any of this current that goes negative here is actually going back to the capacitor. And again, this motor is about 5 ohms, so you get a little I squared R. Plus, you get the IR drop, so voltage drop based on, there it is right there. So while you're accelerating, your back EMF is bumping into the voltage limit. That's fine. You're just bumping your head a little bit. It's okay. But over time, if you're constantly voltage limited, you better slow down. Maybe not so much acceleration to chew up the remaining energy either. But again, this drive operates all the way down to 14 volts. You'll just get an under voltage shutdown. You can still talk to the drive. I know these UltraCAPs tend to come back a little bit, so I'm not sure if the load is, if it's sufficient enough to prevent it from coming back. That's why they store these things with shorts on them, because they kind of charge themselves up a little bit. And the last thing I can think of is, maybe the Nano operates down to 9 volts, and I'll test that next time when I get it hooked up. Okay, thanks for watching. UltraCAP battery charge systems for mobile vehicle applications, and the ME3, one of the most efficient drives for 3 axes of motion control.